Hello, welcome to our channel for probability and statistics. In this video, we'll talk about tests for linearity of regression model. So test for linearity also means test for model appropriateness. Because in linear regression, in a simple linear regression, for example, we assume that there is no second power of the independent variables in the model. So if say we omit some very important information which come from the second or third power of one of the independent variables, so we say the model is not appropriate and the model is not linear in terms of the variables. So how to test for the appropriateness of the model? So one way is using repeated observations. So this means in a given x variable, in a given independent variable's value, we will test and get several observations of y. So say for x1, x2, until xn, and we get ni for each of these xi's values, observe the value for the y. So say for example x equals x4 for given value of independent variable, and we get 3 measurements of y. So we denote Ti dot equals the sigma of odd y values for this given x value. Then we divide it by this ni, we get the mean of yi dot. So this value is the mean value for given xi's y value. So we need this value because for the given xi, so x is fixed, but we get a different y value. So this difference from the y value is the pure random variable. So this is a pure random variable and is not connected with the model. It's not connected with the modeling because we need a pure randomness in testing for linearity. So, in the linear regression, we get the fitted model, fitted line, and we have the real observations. The difference between these two is called error term. And actually, this error term is a combination of pure experimental error and another term which is called lack of fit contribution. So lack of fit error, if it's very big, so the model is not appropriate. So we hope the lack of fit error is as small as possible. I'll say the most of the errors come from pure experimental error. And this pure experimental error, we have used repeated observations to test. So next, we will denote several important items. So this Si is actually the sum of error terms for given xi's y variable, right? So for one of xi independent variables value, we get odd y value, then minus this y bar for the given xi. Then take a square and divide it by ni minus 1. So this is called Si square, and we sum all the Si squares, then putting this odd Si and divided by n minus k. So we get this Si is the real pure random errors SI. So if we look back one page, so in the real, if the model is correct, then all the SI, S square, comes from the pure random error. And this term will actually equals SSE divided by n minus 2. So SSE comes from the sum of error squares using the difference between observations and fitted value. So SSE divided by n minus 2 in a correct model is the same as S square. S square is a pure random error item. So these two will be equal. And SSE and this item comes from SSE divided by n minus 2 will be an unbiased estimate of sigma square, which is the model's error term. But if the model is not correct, if we omit some second power terms or third power terms, then this two is not correct. This is not correct. So we use this table will be more clear for the idea. This is SST, the total sum of square. If we have learned the basics of linear regression, you know this term actually is the sum of difference between y observations and y mean values, or sum of these differences square. So this is SST, and it has degrees of freedom n minus 1. So this table is like an ANOVA table, analysis of variance. And SST has two parts. One is SSR, another is SSE. SSR is sum of variation due to the model, due to regression. So this is the term of the value on the fitted line and between this item and the mean value of y. So this term has 1 degree of freedom. Another is SSE. SSE we have said that is the difference between the observations and the fitted value. So SSE and SSR combined is SST. So now we will focus on these two lines. So if the model is not being done correctly, so SSE will have two parts. One is SSE we call pure. This is the same as we have shown in the previous page that we use repeated observations for given x value. So this is SSE pure comes from the repeated observations, pure randomness. And another part is SSE minus SSE pure. So this is the lack of fit item. So this is all their corresponding degrees of freedom, and this is the item divided by its corresponding degrees of freedom. So in a real model, in a real correct model, we can use these two is for the f value. If the model is correct, we just use this to test if the model is significant, or say the odd independent variables can explain the model, like something that. But now we focus on these two parts. So S square is SSE pure divided by its degrees of freedom. And SSE and the lack of fit is the difference of these two parts and divided by its degrees of freedom. So this part is the f value because these two parts both have chi-square distribution with degrees of freedom. And division of these two parts divided by their corresponding degrees of freedom will follow an f distribution. If if this part is very small. Under the assumption we will test this part. So the null hypothesis is lack of fit is very small, is 0. So under this assumption, this term will follow F distribution with these 2 degrees of freedom. So if this F test is significant, then we will reject the null hypothesis and this term will not be 0, which means the model is not fit good, right? We have omitted some important items in the model. So this test is significant, which means the model is not appropriate. So next we will show an example. So this is data, all the x values and all the y values. So you can see for the given x value, we have repeated observations for the y. Then we will test if the model is fit correctly. So we just calculate all the items in this ANOVA table. So the result is this one. This is the F-test result. You can see the p-value is quite large and much larger than 0.05. So the test is not significant and we will not reject the null hypothesis of lack of fit is 0. So which means the model is correct, right? Because the test is not significant and this lack of fit is very small compared with the pure error term. Thanks for watching.